Okay, we're in Appendix C, golden ratio and Fibonacci numbers, all right? So one thing I want to point out is there's connections, and we'll talk about those connections are between the two. This is an interesting equation to solve, and I'll write this down for you. It's x equals 1 plus 1 over x. Multiply both sides by x, you get x squared. X plus 1, x squared minus x minus 1 equals 0. Let's keep going. Quadratic formula, x equals, relatively simple. What goes on bottom? Twice the coefficient of the square term, which should be 2. The opposite, this is what goes on top, the opposite of the coefficient of the linear term, which is 1, plus or minus the root. The coefficient on the linear term squared, which would be 1, minus 4ac. I'm sorry, I shouldn't say a, the coefficient, because there's no a there. 4 times, when I said there's no explicit a, 4 times the coefficient of square term, which is 1, so it's 4, and times the constant term, which is minus 1. So it's minus a minus 4, which is plus 4. So we give your x equals 1 plus or minus the root of 5 over 2. Now, one thing nice about this, you should recognize, or maybe recognize, I should say, that one of these numbers is pretty famous, that 1 plus the root of 5 over 2 is given a symbol phi, and that's called the golden ratio. All right? Now, that's one way to get it. We got the golden ratio there. If you go back to section 108, there's another discussion of the golden ratio as it relates to continued fractions. What I want to do is I want to use this equation over here and gently say, okay, x is phi, so I'll write that down. That's right over here. And then I make a guess on it, all right? So I'm going to say my first guess, phi 1 is 1, right? I'm going to write as a ratio 1 over 1. And what would the second guess be from this one over here? I kind of just plug it back in, putting it 1 plus 1 over 1. That's the reciprocal of the prior term, by the way, which should just be 2, or 2 over 1. All right? Let me tell you where this is. We got this. We got this. Start writing other ones down. 1 plus the reciprocal of the prior term, which is a half. What does that give me? Let's see, 2 plus 1 is 3 halves, right? Let me show where that is. Let's go to the next one. Reciprocal of the prior, which is 2/3. That's going to be 5/3. Show where that is. Let's go to the next one. 1 plus the reciprocal of the prior term, 3/5. That's going to be 8/5. Show where that's written down. Let's go to the next one. You notice when I typeset something, it looks better than when I do chicken scratch. That's important. What do you have here? 1 plus, that's going to be 5/8 now, right? Let's see, 8 and 5, that's 13/8, right? That's right over here. And you could do this all day long, by the way. Now, what I'm going to claim, you write it down as a listing, and when you write things down as a listing, it might be more apparent what we're looking at, all right? So I want to point out what we just generated. We generate a bunch of these guys over here. There's that line. We got this one, 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 we got this one. My claim over here is there looks like a pattern to it. And certainly looking at this, I'm hoping the pattern's sort of obvious. Let's go through this one step at a time. 1, 1, 2, 2, 3, 3, 5, 5, 8, 8, 13, 13, 21, 21, 34, 34, 55, 55, 89, 89, 144. You get the idea. Let me get my eraser out. I definitely see that. Question is, where this number's coming from. Let's take a look at it. And I'm going to say it's these guys here that generate all future terms. And why is that? It's an iterative process. We started out with 1. We wrote it as 1 over 1, and we iterated. We just kept getting the next one, the next one, the next one, the next one. So I'm going to claim over here, if you took those two numbers and added them together, 1 plus 1 is 2, that's where I'm getting that 2 from. And 2 plus 1 would give me 3. And 3 plus 2 would give me 5. And 5 plus 3 would give me 8. 8 plus 5 gives me 13. 13 plus 8 gives me 21. 21 plus 13 is 34. 31 and 21 is 55. You get the idea. This goes on and on and on and on and on and on and on, and it goes on forever. All right, now what I did over here was I graphed those fractions. For example, the first fraction I graphed is 1 over 1. That's right over there. The next fraction I graphed was 2 over 1, right over here. The next fraction I graphed was 3 over 2, which is about 1.5, right over there. So forth and so on. And I graphed out a bunch of them up to the 24th term. I did that. Now, of course, I'm going to blow this up. And I want to point out, it looks like they're settling onto a line, right? They look linear. Not in the beginning, but over time, I'm going to say by the 7th one, you can't tell the difference between the point and the line. Now, granted, there is a difference. You just don't see it because the artifact of the graph, I mean, you see them in the beginning. There's a difference between the point and the line, definitely. Even with this point's below it, this point's above it. At this point, though, it looks like it's directly on the line. And everyone there on out looks like it's directly on that line. Question is, what's that line? That line is y equals, whoops. Let me tell you what that line is. Get the eraser out. This red line over here is the golden ratio. What's the golden ratio? It's simply just y equals 1 plus root 5 over 2, which is our phi, all right? All right, we got that. Now, granted, I'm not expecting students to go through this part over here, the linear algebra part, but something interesting happens when you go through the linear algebra part. Yeah, you still generate the same sequence, but you get this formula for the Fibonacci number. It's Benet's formula. All right, so I want to go through a few of them. I'll put F0 down for you. That's going to be 1 over root 5. N is 0, by the way. So this would be 1 minus 1, which should be 0. Got that. Let's do f of 1. That's 1 over root 5. And what do you get there? 1 plus root 5. I'm just putting n equals 1 now. And if you simplify that, what do you get? 1 over root 5. Whoops, sorry about that. 2. Now it'd be 2 root 5s. Well, if you did that, you just get 1 in this over here. And you could keep doing this over and over again. What's nice about this formula, though, you don't have to write every single term down. For example, if you wanted F18, you would just plug in n equals 18 over here. Now, granted, it's a difficult computation, but you can still do it. Certainly, a computer could do it quite rapidly. Again, known as Benet's formula. Right, going back to section 108 of these notes over here, this is section. You may recall, or you may want to go back and review it, we did continued fractions. And the golden ratio has a very nice continued fraction form. All right, very nice continued fraction. Again, you may want to go back and review that section. This was just an introduction to the golden ratio and its relationship to the Fibonacci sequence. Thank you for paying attention.